October 29, 1943. Normandy airspace, 14:37 hours. The Rolls-Royce Merlin engine screamed at 3,000 revolutions per minute as Captain Robert Hollis pushed his P-51B Mustang through a banking turn over occupied France. Below him, the patchwork fields of Normandy spread like a torn quilt. His mission was simple: long-range escort for B-17 bombers returning from Bremen. But simplicity ended when black smoke began pouring from his cowling. German flak had found its mark. Hollis felt the aircraft shudder. Oil pressure dropping. Temperature rising. The Merlin, that magnificent British-American hybrid engine, was dying. He had minutes, perhaps seconds, before catastrophic failure. Through his canopy, he could see German fighters circling like sharks sensing blood. The radio crackled with urgent voices, but Hollis was already too low, too far behind enemy lines. "This is Mustang 27. I'm going down." Grid reference Baker 4-3. The words were calm, rehearsed. But his hands trembled on the stick. What Captain Hollis didn't know, as he prepared for a controlled crash landing in a field near Abbeville, was that his aircraft, serial number 43 to 12093, would become one of the most important intelligence prizes of the European War. The Germans had shot down Allied fighters before. They had captured Spitfires, Thunderbolts, even early Mustangs. But this particular aircraft, with its laminar flow wing and that revolutionary engine installation, would end up on a steel examination table in Rechlin, Germany's premier aviation test center. And when Luftwaffe engineers finally cracked open that engine cowling and saw what lay beneath, their understanding of Allied aerial superiority would fundamentally change. They would discover an engineering philosophy decades ahead of German thinking, a philosophy that prioritized cooling efficiency, power-to-weight ratios, and manufacturing simplicity in ways that challenged everything they thought they knew about piston engines. The war in the air was about to become a war of engineers. Hollis brought the Mustang down hard in a farmer's field, the propeller chewing earth and grass before the aircraft skidded to a violent stop. His head slammed against the canopy frame despite his harness. Blood trickled from his temple. The acrid smell of burning oil and hydraulic fluid filled the cockpit. He had perhaps 2 minutes before German soldiers arrived, maybe less. He reached for the destruction charges. Standard protocol required pilots to destroy their aircraft to prevent enemy intelligence gathering. But his hand hesitated over the toggle. The charge was small, designed to destroy instruments and the gun sight. The airframe would survive. The engine would survive. And Captain Hollis, bleeding and disoriented, made a decision that would haunt him for years. He evacuated without pulling the trigger. Within 15 minutes, a Wehrmacht patrol surrounded the downed Mustang. Within an hour, technical specialists from Luftflotte 3 headquarters arrived. Within 3 hours, a secure telegram reached Rechlin Air Base, American long-range fighter captured intact. Engine appears undamaged. Recommend immediate technical recovery. The field telephone in Major Wilhelm Willi Storr's office rang at 1900 hours. Storr, chief of enemy aircraft analysis at Rechlin, listened intently to the description from the field officer. His eyes widened. "Intact. You're certain the engine is intact?" "Yes, Herr Major. Oil leak, but no catastrophic damage. The pilot attempted no sabotage." Storr's mind raced. They had examined captured Mustangs before, early A-36 variants with Allison engines. Competent aircraft, nothing revolutionary. But intelligence reports suggested newer variants carried British Merlin engines, the same power plants that had given Spitfires such troublesome performance at altitude. If this was true, if they could study the American installation methods, the cooling systems, the supercharger integration. "Secure the site," Storr ordered. "I want armed guards around that aircraft until transport arrives. No one touches it. No one." He hung up and immediately drafted orders for a specialized recovery team. The Mustang would be transported by rail to Rechlin within 48 hours. The chase had begun. To understand what the Germans were about to discover, we must travel backward 18 months to Inglewood, California, to North American Aviation's sprawling factory complex where the P-51 Mustang was being transformed from a promising airframe into a legendary weapon. The original P-51, powered by the Allison V-1710 engine, was fast at low altitude but disappointing above 15,000 feet. The British Royal Air Force, desperate for aircraft in 1942, had tested the early Mustangs and recognized the brilliant aerodynamic design, but identified the engine as its fatal weakness. A radical suggestion emerged from Rolls-Royce test pilot Ronald Harker: install the Merlin. The Merlin 61, with its two-stage, two-speed supercharger, was already proving devastating in the Spitfire 9. But marrying a British engine to an American airframe presented enormous challenges. Cooling systems had to be redesigned. Engine mounts required complete re-engineering. The propeller shaft alignment, the exhaust system, the oil coolers, everything changed. American engineers, led by chief designer Edgar Schmud, approached the problem with a philosophy that differed fundamentally from German practice. Where German designers often prioritized absolute performance and accepted complexity, American engineers obsessed over mass production, maintenance simplicity, and thermal efficiency. The Packard-built Merlin V 1650-3 that would power the P-51B represented this philosophy perfectly. The cooling system was revolutionary. Instead of traditional chin-mounted radiators that created massive drag, Schmud's team designed a ventral scoop that used the Meredith effect, a thermodynamic principle where heated cooling air actually generated thrust as it exited the aircraft. The radiator wasn't just a necessary evil, it became a net contributor to speed. The supercharger installation prioritized reliability over ultimate boost pressure. The intercooler system used an innovative dual-pass design. The reduction gearbox employed helical gears that German engineers would find fascinating in their precision and quietness. But most importantly, every component was designed for replacement in field conditions. Where a Luftwaffe ground crew might need 8 hours and specialized tools to change a Daimler-Benz engine, a trained USAF crew could swap a Merlin in under 4 hours using basic equipment. This was industrial warfare thinking. This was the American way. November 2, 1943. The damaged P-51B began its journey to Germany under heavy guard, loaded onto a specialized Reichsbahn railway flatcar. Wehrmacht security personnel accompanied the train, under strict orders. The aircraft was classified as Kriegswichtig Sonderstufe, war-critical special grade. Any partisan attack was to be repelled with maximum force. The train moved slowly through occupied France, through Belgium, across the Rhine into Germany proper. At each stop, curious Luftwaffe officers appeared, wanting glimpses of the silver American fighter. Most had never seen a Mustang up close. Its lines were sleek, almost sensual compared to the angular brutality of Messerschmitt or Focke-Wulf designs. The laminar flow wing, smooth and uninterrupted, looked impossibly thin to eyes accustomed to thick-sectioned German wings. Major Storr met the train personally at Rechlin Station. He walked around the aircraft slowly, saying nothing, his engineer's eye cataloging every detail. The engine cowling showed impact damage from the flak hit. Good, that meant the engine had not been run to destruction. The cockpit appeared untouched. Better still. Get it into Halley 7 immediately, he ordered. I want Hauptmann Bauer's propulsion team ready in 1 hour. Full photographic documentation before we touch anything. Rechlin Air Base, located in Mecklenburg, was Germany's equivalent to America's Wright Field, the nerve center of Luftwaffe technical intelligence and flight testing. Every captured Allied aircraft eventually arrived here. Soviet Yaks and Lags, British Lancasters and Mosquitoes, American B-17s and P-47s. Each was meticulously examined, test-flown if possible, and dissected for technical intelligence. But the P-51B would receive special attention. Halley 7 was Recklin's secure examination facility, a massive hangar with overhead cranes, precision measurement equipment, and photographic stations. As workers carefully wheeled the Mustang inside, artificial lights blazed to life. Photographers began their work, documenting every panel, every rivet, every access point. Hauptmann Karl Bauer, Recklin's chief propulsion engineer, arrived with his team of specialists. Bauer was 47, a veteran of the Great War, a man who had designed components for BMW radial engines in the 1920s. He understood power plants the way a surgeon understands anatomy. He approached the Mustang's nose, placed his hand on the cool metal cowling, and smiled. "Gentlemen," he said quietly, "let us see what the Americans have built." November 3, 1943. 8:30 hours. Halley 7. Bauer's team worked with surgical precision. Each cowling panel was photographed from multiple angles before removal. Each fastener was examined and catalogued. German engineering thoroughness was legendary, and nothing would be missed. The first surprise came within minutes. Herr Hauptmann, called Oberfeldwebel Richter, a specialist in fastener systems, these quick-release fasteners, they're extraordinarily simple. Bauer examined the Zeus fasteners securing the cowling panels. Quarter-turn fasteners, spring-loaded, requiring only a basic screwdriver. German aircraft used complex screw systems that required specific tools and careful torque settings. These American fasteners could be operated by any mechanic in seconds, even wearing thick gloves in winter conditions. Practical, Bauer muttered. Very practical. As the cowling panels came away, the Packard Merlin V1650-3 was gradually revealed. The team fell silent. Even to inexperienced eyes, this was an extraordinary piece of machinery. The engine sat low in the airframe, tilted slightly, its liquid cooling system integrated with elegant simplicity. But it was the details that stunned the German engineers. The ignition system used shielded wiring throughout, radio interference suppression built in from the start, not added as an afterthought as in German practice. The fuel injection system was accessible from multiple angles. The supercharger housing gleamed with precision machining. And everywhere, there were inspection plates and quick-access panels. Lieutenant Hans Mahler, the youngest member of Bauer's team but a specialist in thermodynamics, was examining the cooling system. His hand traced the lines of the coolant radiator installation, positioned in that unusual ventral scoop beneath the fuselage. "This is wrong," he said suddenly. Bauer looked up sharply. "What is wrong?" "The radiator position, Herr Hauptmann. The airflow mathematics are wrong. This placement should create enormous drag. The aircraft should be slower, not faster. Unless..." Mahler's voice trailed off as understanding dawned. His face went pale. "Unless they're using Meredith's theorem. Unless they're extracting thrust from the heated cooling air." Bauer moved quickly to examine the radiator installation himself. His experienced eyes traced the inlet geometry, the internal ducting, the carefully shaped exit. The Americans hadn't just installed a radiator. They had designed a ramjet effect that converted waste heat into forward thrust. "Unglaublich," Bauer whispered. "This is decades ahead of our thinking." November 4, 1943. The Packard Merlin was removed from the airframe using overhead cranes, carefully lowered onto a specialized examination stand. Now, separated from the aircraft, the engine could reveal its secrets fully. Bauer's team began systematic documentation. Every measurement was recorded. Every component was photographed. A technical artist, Gefreiter Wilhelm Kunst, created detailed cutaway drawings as the engine was progressively disassembled. These drawings would later prove invaluable, and would survive the war to influence post-war German aviation development. The supercharger assembly came off first. The two-stage, two-speed design was already known from captured Spitfires, but the American installation revealed subtle differences. The intercooler was more compact, using a different coolant flow pattern. The reduction gearing showed incredibly fine tolerances, better than German production standards despite being manufactured for mass production rather than hand-fitting. How do they achieve this precision at scale? Mahler wondered aloud. "Our BMW 801 requires individual fitting and adjustment. This appears to be assembled from interchangeable parts." Bauer understood immediately. The Americans had invested enormous resources in manufacturing technology, precision jigs, standardized tooling, quality control systems that ensured every component met specifications without hand finishing. German industry, despite its reputation for quality, still relied heavily on skilled craftsmen making individual adjustments. The American approach was less artisanal but far more scalable. The crankshaft was particularly revealing. Forged from a single billet of high-alloy steel, balanced to extraordinary precision, it showed a level of manufacturing sophistication that impressed even these veteran engineers. The connecting rods used advanced metallurgy, a chromolybdenum alloy that German intelligence had underestimated in strength. But the revelation that shook Bauer came when examining the cylinder heads. The valve arrangement was conventional, 4 valves per cylinder in a hemispherical combustion chamber, nothing revolutionary there. But the cooling passages showed a level of thermal management sophistication that German designs lacked. Every surface that experienced high heat loads was bathed in coolant flow. The exhaust valve seats had additional cooling channels. The spark plug bosses were designed to shed heat efficiently. "They've obsessed over cooling efficiency," Bauer told his assembled team during an evening briefing. "Every decision prioritizes thermal management." Why? It was Mahler who provided the answer: reliability, Herr Hauptmann. An engine that runs cooler runs longer. It requires less maintenance. It can be pushed harder without failure. Bauer nodded slowly. They're building engines for operational availability, not just peak performance. They're building engines for a long war. The implications were sobering. November 6, 1943. Bauer compiled his preliminary report in the cold hours before dawn. His hands trembled slightly as he typed, not from cold, but from understanding. The Packard Merlin V 1650-3 weighed 1,645 pounds and produced 1,380 horsepower at 3,000 revolutions per minute. Germany's premier fighter engine, the Daimler-Benz DB605, weighed 1,764 pounds and produced 1,475 horsepower. Similar specifications on paper. But the American engine achieved its power with greater reliability, required less maintenance, and was manufactured at a rate of 200 engines per day across multiple factories. 200 engines per day. The Daimler-Benz factories, constantly targeted by Allied bombing and struggling with labor shortages, were producing approximately 1,200 DB605s per month, barely 20% of American Merlin production. And the American engines didn't require the extensive hand finishing that slowed German production. But raw numbers told only part of the story. Bauer's report highlighted more troubling discoveries. Cooling system philosophy. The Americans had designed the entire aircraft around optimal cooling. The Mustang could cruise at high power settings for extended periods without overheating. German fighters required constant throttle management to prevent thermal damage. Maintenance design. Every major component could be accessed or replaced with basic tools. The engine could be removed and replaced in under 4 hours by trained crew. German engines required specialized equipment and 8 to 12 hours. Fuel system. The Mustang's fuel injection system was simpler than German designs, yet more reliable. It used fewer precision components and showed greater tolerance for fuel quality variations. Supercharger efficiency. The two-stage supercharger maintained high manifold pressure at altitude without the excessive heat generation that plagued German systems. Bauer leaned back in his chair, lighting a cigarette with shaking hands. The smoke curled upward in the dim light. Outside, he could hear the distant rumble of Junkers Ju-88 night fighters returning from missions over the Reich. How many would not return tomorrow? How many were being lost because German fighters couldn't effectively escort or couldn't maintain patrol at altitude where American bombers operated? The door opened. Major Storr entered, his face drawn with exhaustion. "Your preliminary report, Karl?" Bauer handed him the typed pages. "It makes for difficult reading, Herr Major." Storr read in silence for several minutes. His expression darkened. Finally, he looked up. "Can we replicate any of this?" Bauer's laugh was bitter. "Which part? The manufacturing precision that requires machinery we don't have? The exotic alloys we can't produce in quantity? The engineering philosophy that requires complete redesign of our power plants? That bad? Worse. We're not just behind in technology, Willie. We're behind in thinking." November 9, 1943. Bauer had requested permission to repair the P-51B and conduct flight tests, standard procedure for captured enemy aircraft. But the oil system damage was more extensive than initially assessed. The Merlin had ingested metal fragments from the flak hit. Internal bearing surfaces showed scoring. Repairing the engine would require parts that didn't exist in Germany. Still, even a non-flying example was invaluable. The Rechlin team continued their examination, now focusing on the airframe integration. The laminar flow wing was particularly fascinating. Its smooth surfaces and precise shape maintained airflow stability at high speeds. German engineers had explored similar concepts but abandoned them as too difficult to manufacture in wartime conditions. "The Americans are manufacturing these wings by the thousands," Mahler observed. "How?" The answer lay in tooling and quality control. American factories used enormous hydraulic presses and precision jigs that could stamp wing sections to tolerances of hundredths of a millimeter. German production relied more on skilled sheet metal workers hand-forming components. The American approach was less flexible but vastly more repeatable and scalable. Every examination revealed the same pattern. American designs prioritized mass production, field maintenance, and operational reliability over absolute performance. A German fighter might have slightly higher speed or rate of climb, but it would spend more time in maintenance, require more specialized support, and be produced in smaller numbers. The philosophy extended beyond engineering into logistics. The P-51 was designed to operate from primitive forward airfields. Its wide-track landing gear was forgiving for inexperienced pilots. Its system's redundancy meant battle damage often didn't result in loss of the aircraft. Its long range meant it could escort bombers deep into German territory and return. Hauptmann Dieter Vogel from Recklin's Tactical Analysis Section visited Halle 7 to examine the captured Mustang. Vogel was a former fighter pilot, grounded after losing his left hand over Malta. He walked around the aircraft slowly, taking in every detail. "This is the aircraft we're fighting?" he asked quietly. "Yes," Bauer confirmed. "And there are thousands of them?" Production reports suggest over 3,000 by year's end. Many thousands more planned. Vogel was silent for a long moment. "We're going to lose, Karl. That's not my area of expertise." "No. But you understand machines. You understand production. This aircraft represents an industrial philosophy we cannot match." Vogel gestured at the Mustang. "They've built a weapon system for total war, simple enough to mass-produce, reliable enough to maintain under field conditions, effective enough to achieve air superiority. We've built boutique fighters that require craftsmen to maintain." Bauer had no answer. Both men stood in silence, looking at the silver American fighter gleaming under the harsh lights. November 15, 1943. Bauer's complete technical report, 124 pages with detailed photographs and measurements, was forwarded through official channels to the Reichsluftfahrtministerium, Reich Aviation Ministry, in Berlin. Copies were sent to Daimler-Benz, BMW, and Junkers for review. The conclusions were stark. Allied fighter development, particularly American, has achieved a synthesis of performance, reliability, and manufacturability that represents a fundamental advantage in sustained air operations. German fighter programs prioritize peak performance characteristics at the expense of operational availability and production scalability. This approach may prove strategically unsustainable. The report recommended immediate reforms, simplified engine designs, greater emphasis on cooling efficiency, redesigned maintenance access systems, and above all, acceptance that mass production required engineering compromises that would improve rather than degrade overall effectiveness. The response from Berlin was swift and disappointing. Dr. Ernst Heinkel, the legendary aircraft designer, dismissed the findings. "The Mustang is merely a competent design utilizing British engine technology. Our FW-190 remains superior in most performance metrics." He ignored the sections discussing reliability and maintenance. Willy Messerschmitt's response was even more dismissive. "American aircraft are built by workers who understand production but not combat. Our pilots prefer our aircraft." He apparently didn't read the sections documenting German pilot losses to American fighters. Only a few voices supported Bauer's conclusions. General Major Adolf Galland, commander of Luftwaffe fighter forces, had been requesting long-range escort fighters and more reliable power plants for months. Bauer's report provided technical validation for Galland's operational concerns. But Galland was increasingly at odds with Göring and the Nazi hierarchy. His voice carried less weight than it should. The industrial representatives were more receptive but fatalistic. Daimler-Benz engineers acknowledged the American advantages in manufacturing but cited resource shortages, bombing damage, and labor issues as insurmountable obstacles. BMW's response noted that retooling factories for new engine designs would reduce current production for at least a year Germany couldn't afford. By December 1943, Bauer's report was filed away, its recommendations largely ignored. The captured P-51B remained at Rechlin, occasionally examined by visiting officers but generating no meaningful policy changes. The bureaucratic inertia that would contribute to Germany's defeat had reasserted itself. Bauer, exhausted and disillusioned, requested a transfer to a frontline maintenance unit. He felt he could contribute more directly there. The request was denied. He was too valuable at Rechlin, analyzing enemy aircraft that German industry couldn't or wouldn't match. In February 1944, he would watch from the ground as formations of P-51 Mustangs, hundreds of them now, escorted bombers over Rechlin itself. The silver fighters circled overhead, untouchable, demonstrating the very supremacy his report had warned about. The captured P-51B remained at Rechlin until April 1945, when advancing Soviet forces captured the facility. The aircraft itself was likely destroyed in the final chaotic days. German personnel burned or sabotaged most equipment to prevent Soviet acquisition. But the documentation survived, scattered across multiple archives. Captain Robert Hollis, the pilot who had crashed that October day in France, spent the remainder of the war in Stalag Luft 3. He survived, returned home to Texas, and never spoke publicly about his failure to destroy his aircraft. In 1956, during a veterans gathering, he finally learned that his captured Mustang had been extensively studied by German engineers. Did it help them? He asked quietly. The answer, no, not really, provided small comfort. Hauptmann Karl Bauer survived the war. He was briefly detained by American forces during the occupation, but was quickly released when his role as a technical analyst was clarified. In 1948, he immigrated to Argentina, where he worked for the nascent Argentine aircraft industry. He never returned to Germany. He died in 1971, leaving behind technical notebooks filled with drawings of the American aircraft he had examined, including detailed sketches of that remarkable Packard Merlin engine. The lessons from the captured P-51B influenced post-war aviation development globally. German engineers who had studied Allied aircraft carried those lessons into the jet age. The philosophy of designing for maintainability, of prioritizing thermal management, of accepting some performance compromise for reliability, these American approaches became standard practice. The broader lesson was strategic. In industrial warfare, the ability to produce and maintain thousands of good aircraft proved superior to producing hundreds of perfect ones. The Mustang wasn't the fastest fighter of World War II. It wasn't the most heavily armed. It wasn't the most maneuverable. But it could be built quickly, maintained easily, and operated reliably, and there were enough of them to achieve air superiority. When German engineers opened that P-51 and found an engine built decades ahead of its time, they weren't just discovering superior technology. They were discovering a different philosophy of warfare, one that valued operational availability over technical perfection, one that understood logistics as thoroughly as aerodynamics, one that recognized that wars are won not by individual technological marvels but by sustained industrial production. The silver Mustang on the examination table represented something the Third Reich could never replicate: American industrial philosophy applied to total war. By the time German engineers understood what they were looking at, it was already too late. The war in the air had been decided not in dogfights over France, but in the design decisions made in Inglewood, California, where engineers chose simplicity over complexity, reliability over peak performance, and mass production over perfection. It was a lesson learned too late, paid for in blood, written in the scattered wreckage of 1,000 German fighters that fell from the sky.